This talk is on the structure of minimum vertex cuts. This is joint work with Longhui Yin. So one of the big themes running throughout graph theory is to understand the cut structure of graphs. So let's look at some exemplary theorems in this line of work. So Gomery and Hu proved that if you have a weighted undirected graph, you can represent all n choose 2 minimum ST cuts with a tree. So this is an example of a weighted graph. So any two vertices can take the role of source and sink here. And if you look at, let's say, the minimum cuts separating C and D, the capacity of the minimum cut is 6 right here. And in the corresponding Gomery-Hu tree, the corresponding minimum cut between C and D is 6, corresponding to this. And this tree is cut equivalent in the sense that on one side of the cut in the tree is C and E, and that corresponds exactly to one side of the cut in the actual graph. Okay, so this says that the cut structure can be sparsified in these graphs to in a very effective way, represented as a tree. Another example is the cactus representation, which represents global min cuts and represents all of them simultaneously. So here's an example of a weighted undirected graph. Unmarked edges have weight 1. And you can see in this graph that the minimum edge cut has value 4. Okay, and not only that, but there's many 4 edge cuts in this graph. So these look rather complicated, but they can actually all be simultaneously represented as a cactus, which is a tree of cycles, or a graph in which every edge appears in exactly one cycle. So for example, this cut here is represented in the cactus by cutting 2 edges, namely these 2. So every 2 edge cut in the cactus corresponds to a minimum global edge cut in the original graph. Another example is the Picard-Keren representation for all minimum ST cuts in a directed graph, where S and T are fixed. So here is an ST flow network, and the cut value in this network is 18, and there are numerous minimum directed ST cuts. And the Picard-Keren representation says that each of them corresponds to a downward closed set in a certain graph. So for example, this is a downward closed set. It's derived from everything reachable from the vertex marked B, and that corresponds to this cut in the original graph. Okay, so any downward closed set that separates S and T corresponds to a minimum ST cut. So the purpose of this talk is to look at minimum vertex cuts in unweighted graphs. So we're looking at the cardinality of the minimum size set of vertices that, if you removed it, would disconnect the graph, and we're going to call that kappa. So when kappa equals 1, you can represent the connectivity of the graph by just figuring out what the articulation points in the graph are, the vertex cuts, and those partition the edges into 2 vertex connected components. Okay, kappa equals 2 gets more interesting. In the 80s, Di Battista and Tomasia constructed the SPQR tree. I'll give an example of this. So these gray blobs correspond to 3 edge connected components, and the vertices here indicated are those that participate in 2 vertex cuts. And the SPQR tree basically says how to glue these pieces together to form the entire graph. Whether S roughly corresponds to serial, P corresponds to parallel, and Q and R round out the acronym. Cap equals 3 is similar, but one added twist here is that the series case gets to be a little bit more complicated. You end up with these wheel structures where you have cuts derived by 2 vertices on the outside of the wheel and hub of the wheel, and they form a three vertex cut. But other than that, it's similar in spirit to the SPQR tree. So in 1993, stock 93, Cohen, Di Battista, Konevsky, and Tomasia came up with a structure that sort of is an extension of these first three to any kappa whatsoever, any fixed kappa. And this is it's a 7-page extended abstract, and a full version was never written. And the purpose of this paper, in some sense, as a first step, is to substantiate all the main claims that appeared in this paper, and then go on and look for extensions and applications of these ideas. But basically, to understand the cut structure of minimum vertex cuts for any kappa. Okay, so what do? We come up with a lot of theorems characterizing the cut structure of minimum vertex cuts. And the main theorem is a classification theorem that classifies every 2 vertex cuts, the pairwise relationship of every 2 vertex cuts, as one of 4 categories: wheel, laminar, crossing matching, and small, which I'll get to later. The second contribution is to use this classification theorem to come up with a better data structure for answering connectivity queries. So given 2 vertices, are they separated by a global minimum vertex cut? And if so, return 1 that separates these 2 vertices. And we can answer these queries in optimum time. And to build this data structure, we solve an interesting subproblem here, which is in near linear time to compute the smallest vertex cut separating every vertex from the rest of the graph. By smallest here, I mean the one that kind of lops off the smallest number of vertices containing each target vertex U. Okay, so our vertex connectivity data structure follows some previous work here. I'll just point out some interesting results here. So Izak and Nutov will tell you the pairwise connectivity of U and V up to some threshold k bar, and the size of the labels that they need to answer these queries are linear in k bar and polylog in n. A version of this data structure in the Cohen et al. Paper will distinguish between vertices whose connectivity is kappa versus at least kappa plus 1. And the size of the data structure is roughly kappa cubed times linear. And one contribution here is that we come up with a data structure that is near linear time constructible versus polynomial and exponential in kappa and polynomial in n. It will distinguish between vertices that are kappa connected or at least kappa plus 1 in optimum constant time. And if they are separated by a minimum vertex cut, we'll return 1 in optimum time, and the size of the label is also optimum. So it's a narrower set of queries than some of these previous data structures, but it's optimal in essentially every respect. Okay, so what does this classification look like? So we have 4 categories. Let's go through them one by one. So U here is our reference cut, and we're going to look at the relationship that U has with other vertex cuts here. So here the connectivity graph is 7. So a cut is laminar, a cut W is laminar if all, with respect to U, if all the vertices outside of U are in one side of the cut. Okay, so U is, in this example, separates the graph into 2 sides, we'll call them A and B. And W1 is a laminar cut that intersects U, but is otherwise completely inside B. And cut W2 is a laminar cut with respect to U that is completely inside A. Okay, wheel cuts are a different category. So wheel cuts apply when, let's say, U separates the graph into 2 sides, A1 and A2. W is a cut that separates the graph into 2 sides, B1, B2, and all 4 of these intersecting sets are non-empty. So the picture looks something like this, where U and W intersect at some set T, but the 4 quadrants in these separation sets are all non-empty. Okay, so this is what we would call a 4-wheel, because there are 4 spokes, and you can pack many pairwise wheel cuts into a larger wheel. So sometimes we'll draw wheels that look like this. This would be a 6-wheel, and 6 wheels have the property that they consist of spokes marked with C's here, and sectors, which are marked with S's. And all the spokes have the same size, and there's some hub in the middle. And they have the property that if you pick any 2 spokes, let's say C2 and C4, and the hub, they form a minimum vertex cut. So there's a quadratic number of cuts here implied by the structure of the wheel. All right, so one interesting thing about vertex cuts that is quite different than edge cuts is that whereas there's only a quadratic, n squared number of distinct minimum edge cuts, there can be an exponential number of minimum vertex cuts. And the way these arise in the graph is through a category that we call matching cuts. So the idea is as follows. If you want to create a whole bunch of vertex cuts, let's say with respect to U, you could say, well, let's say U separates the graph into 2 sides, A and B. And inside A, U and its neighborhood form a matching. Okay, so what can you do? You can, let's say, call this cut W here. This is a matching cut with respect to U inside A. This is a very simple matching cut. And you can make an exponential number of matching cuts in this particular example by just choosing any subset of U's neighborhood inside A. Okay, so this is a example to show some, let's say, structured matching cuts that are not too complicated. But in general, we'll say matching cuts are derived by taking some subset of the vertices in U and replacing them with their neighborhood inside of one of the sides of U, let's say A. And when is this possible? So there's a 1-to-1 correspondence between maximum matchings in this graph and flows in a certain ST flow network derived from this bipartite graph. And inside that flow network, there's a 1-to-1 correspondence between maximum flows, minimum cuts, and in the original bipartite graph, vertex covers. And by the Picard-Carén theorem, these minimum ST cuts are closed under unions and intersections. And although there's an exponential number of possible minimum ST flows, they are generated by a relatively small set of vertex sets here, minimal vertex sets that have whose neighborhoods have the same size as they do. So in this particular example, this is such a vertex set. Its neighborhood inside A is 1. This is a vertex set. Its neighborhood size inside A is 2. This is another set here. And then we have nesting sets here, like this. And although there's an exponential in kappa number of matching cuts with respect to this kappa, there's a linear in kappa representation of all of them using this set family closed under union and intersection. All right, so laminar cuts are basically, matching cuts are basically laminar cuts. So in a sense, we've already dealt with this category. So the new category is what we'll call sort of an extension of matching cuts called crossing matching cuts, where the cut might contain some elements in B, but then the matching part only exists between U and one side of U, say A. So here in this example here, we have a laminar cut W with respect to U inside B. And at the intersection of W and U, we have these 3 vertices, and we can apply the same kind of ST flow and matching framework to generate sort of, matching cuts with respect to U and apply this transformation to W. So for example, in this case, you get some, crossing matching cut that includes the neighborhood of these two vertices inside A. And we can have a different crossing matching cut, let's say, that includes the neighborhood of these three vertices inside A, and so forth and so on. Okay, so now we have three categories. So the hard part in this classification theorem is not to list different types of vertex cuts, it's to know when you're done and to say that this list is exhaustive. Okay, so we have laminar cuts, crossing matching cuts, and wheel cuts. And one question you might have is, are we done? Is there anything else to think about, or is this classification all there is? And it turns out there is another category that is a little weird and doesn't seem to have any analog in the edge-weighted, the edge cut world. So here's a little example illustrating how you can have a cut that doesn't fit the ordinary classification. So at first this looks a little bit like a lopsided wheel, but it's not a wheel. So the connectivity of this graph is 4. There's many 4 vertex cuts. Here are 3 of them. And the pairwise relationship between all of these 3 is laminar. But then we have this cut here defined by this semicircular arc. And if you look at the relationship between this semicircular arc and the horizontal cut, it's not laminar, it's not a crossing matching cut, and it's not a wheel cut. So this, we need a new category, or maybe we need 2 new categories, or some number of new categories. So such cuts that look like this, let's say this separates A, which is a single vertex, and let's say B, the rest of the graph. So we're going to call these types of cuts small if the small side, in this case A, which has cardinality 1, if the small side has at most kappa minus 1 vertices. Okay, so structurally we're not saying anything, we're just talking about the cardinality of the small side. Okay, and those are the 4 categories: laminar, crossing matching, wheel, and small. So the binary classification theorem, and here this only applies if kappa is sort of bounded away from n, says that every 2 cuts either have a laminar relationship or they form a 4-wheel, and it might be, that 4-wheel might be inside a larger wheel, but those 2 cuts form a wheel, or they form a crossing matching cut, or the strangest of the 4 classifications, W is a small cut, and all the small sides of W are completely contained inside U, or vice versa. And this is exhaustive. Every 2 cuts satisfy one of these properties. And of course, we go on and prove other structural features of wheels separately, and crossing matching cuts separately, and small cuts separately, and so forth. But this is the main classification theorem. So how do we apply this to some new area? So the application that we come up with is labeling vertices to answer connectivity queries. So let's introduce a little notation for this. When you remove a cut, it disconnects the graph into connected components called sides, and we'll let side V be the side of this cut containing V. So when you fix a vertex V, there's lots of cuts in the graph, and small v, shortened SMV, refers to the one who's such that side V is minimized in cardinality. So we're going to let small v be the minimum cut U that minimizes the side of V in cardinality, as long as it's at most this threshold here. And it turns out this threshold is a very critical number here, that if small v exists, it is unique. And above this threshold, it's not necessarily unique, but at that threshold, it is unique. Okay, so what does the label store? The label stores this small v cut. The label stores the side of the size of the side of V when you remove this small v cut. That side, we'll give it a name. We'll give it a log n bit identifier and refer to this side as some identifier, so we can compare these things for equality. And if this side is actually very small, we'll just store all the vertices on V's side explicitly. Okay, and that's pretty much the label. So how do you answer connectivity queries? We can go through it sort of case by case. We'll take U and V. We'll look at their small cuts. If their small cuts are identical, then the picture may look like this, in the sense that side of U is equal to side of V, and they're all in the same connected component here when you remove small u. If this is the case, then U and V are kappa plus 1 connected, and there's no kappa cut separating them. And this follows from details inside our structural theorem. If the side of U is not equal to the side of V, but they both share the same small cut, the picture can look like this, where the small cut breaks it into two components, one containing U and one containing V, and one containing the rest. And in this case, they're obviously not, they're kappa connected, and you can pick small u as a specific cut separating U and V. Okay. Okay, in another case, small u is not the same as small v, and neither is in each other's cut. Okay, this is a relatively simple picture, so the picture could look like this, or they could be disjoint. But here, this is a more interesting case when they're nested. So V is a vertex, and this is small v, the cut separating it from the rest of the graph. And inside of this is U's side and small u here. So if this is the case, if V does not appear in U's small cut and U does not appear in V's small cut, then we'll just figure out which is smaller, which side is smaller. In this case, U's side is a subset of V's side, so it's smaller. And small u is the cut separating U and V. Another extreme case is when U is in V's cut and V is in U's small cut. And by the structural theorem, this only occurs when they form a four-wheel, and it also implies that there's no kappa cut separating U and V, and in this case, U and V are kappa plus 1 connected. And there's a couple more cases that I won't go into because they follow the same kind of reasoning. Okay, so in conclusion, we substantiated and improved the main claims in Stock 93 extended abstract by Cohen, Di Battista, Kanevsky, and Tomasia. And this paper is about understanding the cut structure in graphs when you look at minimum cardinality vertex cuts. The whole point of this line of inquiry is to come up with better data structures and better algorithms for vertex connectivity in general. And we answered one type of query, which is a pairwise connectivity query, and you find a cut separating U and V if there is one, a kappa cut separating U and V. But there's lots of other queries you could think about that we don't address, but I think our structural theorems will let you come up with efficient solutions to these problems. One natural query is you give the query a list of kappa vertices, and you ask it, do these vertices separate the graph or not? Yes or no? We don't know how to answer this question, but I think the answer should be possible using, once again, linear space like n times kappa space and kappa query time. Another type of query we get to answer is given two vertices, return all the minimum cuts separating U and V. And here we would want to spend linear time in the output size with roughly n times kappa space. Another interesting open problem is we assume kappa is pretty far bounded away from n. So not when the vertex connectivity is not too large. And it may be that when kappa is unbounded, that 4 categories will be insufficient to classify all cuts, or maybe there's a better way to classify all cuts that that perhaps thinks more about the structure of the small class or breaks it into a couple of subcases or something. But anyway, classifying vertex connectivity in the large kappa case is open. Okay, that is the end of my talk.